we have the return of Daqing 1, who will speak about zeta functions of Toric Calabi-Yau hypersurfaces.
Okay, so before I continue the discussion of Newton polygon, maybe I want to review the meaning of the slope, perhaps for the students in physics. For number series is of course redundant, but I just want to refresh your mind in case you forgot what does Newton polygon mean and why we're interested in the slope business. So, remember we have this zeta function, so which is a rational function, has some zero in the pole. And so if we have a family, actually this root depends on, zeta function depends on lambda. If we have a parameter, lambda, then this roots will depend on lambda. Right. So there's alpha I lambda, the actual algebraic integer. So since it's an algebraic integer, so it's a global number, you can view it from many different points of view. The first point of view is viewed as a complex number. So you think of this as a complex number. And then for any complex number, then you can write as its length, which is observarial, times an angle, e to the I, let's say, of lambda. And it turns out, for us, the observarial, the power of Q, and this would be weight of alpha lambda. So from mirror symmetry point of view, you want to understand how much symmetry you can deduce for the L function. Then of course we know this zeta function depends a lot on the parameter. So if you move the parameter a little bit, your zeta function has changed a lot. As in Candela's talk yesterday, he was trying to search for some sort of symmetry for the zeta function of the Calabi-Yau and its mirror. Of course, the weakest possible symmetry is just the hard symmetry, which gives you for his example, the degree of the numerator and denominator, which switch under mirror symmetry. So you want to do something stronger than that, but to do it for the whole zeta function, that's too strong, that doesn't hold. Therefore, you want to look for some invariance which is finer than beta number, finer than Hodge number, which has some arithmetic meaning, which still has some symmetry structure. And the strongest part is this zeta function, which is too strong. So we try to look for other invariants. So because zeta function is determined by these roots. So then we try to look for the invariance of these roots. Now here the roots, you can separate the two parts, the discrete part and the continuous part. The discrete part is given by the observarial, and the discrete part, continuous part is given by the angle. Now, of course, for the complex observarial, it turns out this discrete part is constant. It's basically determined by the Hodge number HPQ. So that doesn't give you any new invariance. So this weight is constant. When you start with a nice family, it's a constant, basically determined by the Hodge number. And then, of course, since this is constant, the only variable is just theta, the angle. Now, if you take the whole theta, that means you're taking the whole root, and then you're taking the whole zeta function. So that means you're taking the strongest form, which doesn't hold. Okay, so this doesn't work. This doesn't give you any new invariance. that is because you're looking at it from a complex point of view, and because this number is actually a global number, it's not a big integer, you can look at it from non-Archimedean point of view, and you can try whether that will give you something finer than Hodge number. And then, of course, there are many non-Archimedean observarial over Q. So if you view this as an analytic number, so L is different from the characteristic P, then it turns out you get even less, because all the analytic observarial is trivial, is 1. So that gives you just a beta number. It doesn't even give you a Hodge number. Okay, good. There's still one choice left for P. So let's look at that case. So we view this algebraic number, embed them into a periodic number. And in this case, again, you can always write a number into the size of this observarial. In this case, will be Q to the, let's say, negative Si of lambda, and times Ui of, there's no I, I'm just starting with 12I, there's no I. Just picking one root. So here U of lambda is a unit. This observarial is 1. So again here, if you take care of you can think of this unit is sort of continuous invariance. So that really basically more determines roots once you know the observarial. So if you keep the unit, then there's not much we can say about it. But that, of course, that will be a further question. And in fact, from periodic point of view, even this unit, you could create a discrete invariance out of that. But let's not just worry about that point. Let's just look at the observarial, the slope. So turns out the slope, which is lambda, which is just the power of Q dividing this eigenvariable, this root. This number, what can we say about this number? This number also depends on lambda. This number depends on your parameter lambda, but in a less severe way, in a milder way only. That's because as lambda vary, your slope, there are only a finite number of possibilities, so it's discrete invariant. It's a rational number, not necessarily integer. So it depends on lambda, but much milder way than the zeta function. So only finite number of possibilities. As lambda varies for fixed family. So the Hodge number, it is finer than Hodge number, because Hodge number also is fixed once you are given the polytope. So that gives you some. This slope is the arithmetic invariant, and if, of course, I'm just talking about the slope of one zero, you really should look at the slope of all the zero, which is the Newton polygon we're talking about. So therefore, this Newton polygon for this L function is a finer invariant than a Hodge number. But certainly much cruder than the zeta function. And furthermore, here, for each p, of course, you have this Newton polygon. Really, you have infinite Newton polygon. But it turns out, again, there are only finite number of possibilities as p vary, because the restriction we had says the vertices of Newton polygon has to be lattice points. So that forces, Newton Parking can vary, but not too much. There are only finite number of possibilities. And the conjecture I mentioned yesterday says that if you have a polynomial over Q, we let P vary, then reduction of the zeta function will be ordinary for infinite many P. That means the lower bound of the Newton polygon will be equal to Hodge polygon, so the Newton polygon will determine the Hodge polygon. But the Hodge polygon doesn't, of course, determine the Newton polygon because the Newton polygon varies. Okay, so this provides the possibility to explore symmetry between slope or Newton polygon. So, okay, that's a review of the meaning of a slope or Newton polygon. Now let me return to the generic Newton polygon. Because Newton polygon it still vary quite a bit, or it's finite. Finite doesn't mean that it is easy. So in my previous lecture, I had this quantity called generic Newton polygon for a given polytope, and there's a prime number P. And we want to know when this is equal to the lower bound, which is Hodge polygon, and for which P this holds. And we know this is a somewhat a complicated problem depending on the combinatorics of delta, also depending on its relation with the prime number P. The exact relation is not clear, although we do have some partial results. And here's my conjecture. So it says there is actually a positive integer depending on the polytope, such that if you look at all the, let's say, all the ordinary prime, means those prime where this equal, we want to basically classify the set, ordinary prime, determine the set. Maybe you want to remove a few small prime because it causes trouble, which may behave irregularly. Let's say d delta, or maybe that's not enough, just some other bigger one. Remove a small number of prime. Then the conjecture says this set should have a very nice structure. This set is basically should be disjoint union of some congruous classes modulo this integer. So this conjecture basically says for any given delta, the generic Newton polygon is ordinary precisely for those prime P in certain arithmetic progressions, except for a few small prime where you may have to rule out. And as a corollary of this conjecture, that means ordinary prime will have a density, which is a rational number. Even that corollary is unknown. What I showed previously just say there is an arithmetic progression which satisfies this property. I did not claim that there's a density. So this will imply much stronger, something much stronger. Anyway, so that is this also implies the density is positive, which of course we know there is a similar conjecture for number field case. If we have polynomial over Q, let P vary, then there's a similar conjecture. The ordinary prime has a density which is positive. And here, we showed that there's at least one arithmetic progression, which is ordinary. So if density exists, it must be positive. It could be smaller than 1, though. I mean, just for even in the case, number field case, you could have 1/2 and 1, the density. So it can be a rational number. It could be smaller than 1. That should be positive. Okay, so that is a general case for arbitrary polytope. Now let's specialize to the case of a reflexive delta where can see a little bit more. And let's see, do we have to? So Candelas reviewed a little bit about the reflexive polytope. So maybe just for number series, just a quick review. What is the definition of the reflexive polytope? So what's the ordinary plan for reflexive delta? So first, what is the ordinary polytope? Suppose you have an n-dimensional integral convex polytope. Then you define a dual polytope to be those points such that sigma xi yi is greater, less or equal to 1, or maybe greater or equal to negative 1, similar. It's true for all y in delta. So of course, delta star is a polytope, but not necessarily integral. It's convex, not integral anymore in general. So delta is called reflexive if delta star is also integral. Then you have, of course, you have delta star is back. So if it's reflexive, you do get a pair of polytope. Then you can ask, how do we know if a polytope is reflexive or not? I think in my notes put on the web, maybe it's sort of faster to put the page here. Is it too small? Too small. Okay, here's the criterion to be reflexive. To be reflexive, for each hyperplane, well, let's just assume zero origin is in the interior of delta. So reflexive means for each codimension 1 phase, the equation is just a linear equation. Is of this form. If you set the right side to be 1, the left side of the coefficient will be just the integer instead of rational number. So that is a that is a criterion to determine it's reflexive or not. All right? And then there's also a notion of what we call a funnel. I don't know whether they still use the same terminology. So delta is called a funnel, which is stronger than reflexive. So reflexive, and the picture, I just draw a picture instead of giving the complete description. So funnel means so you have the unique interior point, it's O or origin. Then for each codimension 1 phase, you connect with the origin. So each delta I is a simplex with determinant 1, that means d of delta I equal to 1. So that's it's called a funnel. This kind of polytope behave particularly nice. Okay, so what can we say about the reflexive polytope? So which prime P is ordinary for reflexive one? Well, we know for generic ordinary, we know for dimension n up to 3, then it's always ordinary. So here's the theorem B. So let delta be reflexive. Now for reflexive, we can just move the dimension, one dimension higher than 1. So if n is less or equal to 4, and it's reflexive, then delta is ordinary for all P. That means the congruence class is the order prime. Okay. And that's the first part. If delta dimension is bigger than 4, or arbitrary dimension, if it's final, then for any dimension it is okay. And delta is ordinary for all P greater than d of delta. Of course, in this case, d of delta is just 7 plus 1. You can compute it. And the idea is just you prove another decomposition theorem, which is stated as a special case. It's called a star decomposition theorem. No, sorry. It's the number of the codimension one phase plus, actually it's equal to number of, it's sorry. This is the number of codimension one phase. That is the case if it's simplex, in addition if it's simplex. Number of codimension one phases. Good, thank you. So how do we prove this theorem? Well, I state a special case. Now prove another decomposition theorem, called star decomposition theorem, which is already the picture which I drew. So you have this reflexive delta with an origin in the interior, unique origin in the interior. Then you form, for each codimension one phase, you connect with origin. So you get this delta I. This is called the star decomposition with respect to the origin. So delta is the decomposition of star from 1 to H. So H will be the number of codimension one phases. Okay, this is a reflexive, delta reflexive. Okay. Delta reflexive. So if P is ordinary for each piece, then P is ordinary for the total. Yeah? So now we can just combine this star decomposition with the previous quadray of indecomposed one. Right. Previously, remember I had a local case where this is equation 1, and there the theorem holds if n is up to 4. So combine that one with this one, then we deduce the first part. Now for the second part, you can just use this one. Because if this is final, then each one has determinant 1. So each local degree is 1. So locally it is true, so this shows globally it is true. So that for the second part as well. Okay. So that is what I know is about the general Newton polygon for reflexive polytope. And then question, which is I do not know, if reflexive delta has dimension 5 or more, let's see. Is it ordinary for OP? So that's something I don't know the answer. It'd be interesting to find out if it's true or not. Probably, I mean, I don't feel very plausible. It could be false. And if so, it would be interesting to find a counterexample. Okay, so far for the general theory. Now let's look at an example which is mentioned in my course description. We specialize to this example, say, what one can prove in this example. What the results apply all the results to this example, so what we can get for this formula of Calabi-Yau variety. So this is a basic example. This family of Laurent polynomial. This is a one parameter family. So its delta will be just convex closure of this lattice point, these vertices, unit vector, coordinate vector. And it is reflexive, so it's dual polytope. It's just the n minus 1 positive n. This is positive n. What is positive n? And then so in two-dimensional case, the picture just look like this. E1, E2, minus E1 plus E2. So this is just reflection of the picture drawn in Candaras talk, because he used the less equal one as the greater. So it's a multiple negative one. You get his one. Of course, the variety is it's the same, torus. Isomorphic. So this one is this delta. And this one, the delta star in this case would be just. So this one is negative 1, negative 1. This would be n, which is 2 minus 1. With origin in the interior. So reflexive, therefore both of them are reflexive. And the first one is, in fact, the better. It's final. Because if you decompose it, each set has determinant 1. And the delta star is not final in general. In fact, it's not final if n is greater than 1. In fact, even for n is 2, it's not final here, because here you have a lot of points here, this triangle. And then when this is ordinary, when this is delta regular, just compute, by example, by definition, it's ordinary. It's a delta regular if and only if lambda is different from one of these value, where alpha is m plus 1 root of unity. So you have to remove a finite number of singular fiber. And the degree of delta is just m plus 1 in this case, which is what I wrote down previously, this example. And then the Hodge number, you can compute the Hodge number. Well, has to be 1 because total adds up into 1. Right. And then what is the Hodge polygon in this case? Well, once you know Hodge number, just put them into, so it would be 1, 1. The slope is 0, 1, 2, 3. Now each side has length 1. So that's Hodge polygon. So the total of this equal to n plus 1. Okay, so this is invariance. Now, what can we say about the L function or Zeta function in this case? So if you apply all the results, we'll put together into a single theorem in this example, and then this one. So I think here it seems to be, because you have this m plus 1 here, so if your prime number divides m plus 1, then it seems there's no regular Brown polynomial, so we have to remove those p dividing m plus 1. So therefore we assume p does not divide m plus 1. Then at least the parameter space is non-empty. In this case, let's say lambda is delta regular over a finite field of course p. And of course, in this case, the L function will be just a polynomial of degree m plus 1. Depending on the parameter lambda. Okay. And for this L function, one can show there's always a trivial 0. So we order these roots. In fact, the first one is always 1. There's a trivial 0. So what's left will be non-trivial. What's left will be non-trivial and pure. Of weight m plus 1. Now you could ask why the weight should be m plus 1 instead of m minus 1, because the dimension of the wire is m minus 1. That's because my L function is sort of it's a zeta function and t times an extra cube, so it's m minus 1 plus 1, plus 2 actually. Q has weight 2, so it's m minus 1 plus 2, which is m plus 1. Later on we remove that factor, so weight will be m minus 1, will be get back to the zeta function case. What? F lambda x is my Calabi-Yau Roland polynomial. This is Roland polynomial. Right. So it's the working with this particular Roland polynomial. One parameter family. At this point, my lambda is actually fixed. Work with the individual one first. Over a finite field. So lambda is an element in the finite field, so that makes this polynomial regular. And then what about, can we say about the slope? Of course, that one is between 1 and n. The rest of it. The slope, well, we know the slope depends on lambda, so we cannot expect the slope is constant. So, but this one is final, this delta. So you can use a star decomposition, decompose it. That will show the generic Newton polygon. In this case, it's ordinary. So because we only have a one parameter family, generic mean it's true for all of them except for finite meaning. So among the regular polynomial, you have to remove a few more. So in this case, generically ordinary. For P, not divided m plus 1. Which means for all, but finite many number, we have the slope. We can order the slope so that each one equal to the slope of the Hodge polygon, which is down here. And each one has length 1, so there's actually only one root with a given slope. So we can order them so that the ith root has a slope exactly I. So here the slope actually distinguishes the roots, but the weight, complex of observer does not distinguish the roots. They're the same, so you can distinguish the roots. So PDK goes deeper because they further distinguish the roots. Of course, from representation point of view, the complex, the Gauss representation in general, this could be irreducible, but from PDK point of view, it's actually reducible. You can go one step further to decompose it. But of course, this decomposition doesn't exist in algebraic setup. It's more transcendental analytic setting. So basically, for a single lambda, except finite many, then you know completely the information about this zeta function, this zeta function in this particular family. You know all the observed value from complex to PDK point of view. And right.
You know how the non-ordinary value represent P?
Non-ordinary value. So for each prime number P, you have to remove a finite number. But that will be defined by another variety, which is called a Hasse variety. It's determinant of the Hasse weight matrix for slope 0, but for higher slope, for each slope there is a sort of a Hasse weight, higher Hasse weight matrix.
But you have a formula.
No, I mean those should be related to some sort of differential equation, maybe a piece of the part, piece of it, and it would be interesting to study those varieties as well. Of course, the points defined by those variety depends on P. So for when P vary, those variety will depend on P. For each P, there is a variety there. It's defined over a finite field. So you want to understand the structure of those varieties. And a further question, which was actually the topic of chapter 3 in my notes. I didn't plan to discuss it, which more or less at this point you could ask, okay, you have settled all the observed value, you have settled it. Now understand the unit parts, the angle. That will be because that's continuous. But anyway, you can ask this question. You can ask, okay, how, first, let's say how the zeta function vary with lambda. Or you can, in this case, because we know that the roots are different, for each I there's a root. So we can also ask how each root vary with lambda. And this question, of course, is now related to the differential equation, to the solution of the differential equation. So that's sort of the chapter 3, which I briefly mentioned some structural results, but it's very sketchy, and I don't understand the differential equation part well myself yet, so I can only speak from a arithmetic point of view. Basically, the zeta function or roots vary continuously from PDK point of view in a certain sense. So there's some sort of analytic continuity variation for both this zeta function and the roots. So, okay. Now, so far I have stated all of these results in terms of the L function, but of course, ultimately you're interested in the zeta function. So it will return So the zeta function which we started, we know of course zeta function is basically determined by the L function, but there's some trivial factor. So let's say we'll put them together after the cancellation. Let's say what is really the primitive part, what is the mysterious part, the primitive part. Let me return to zeta function. So remember, I started with the Rowland polynomial. It's a delta regular over FQ. So I have this L function, which is a polynomial of degree, d of delta, and I said T1 is always a trivial 0, so T1 is a root. It's always 0. So of course you want to take out that one. So therefore, we just remove this trivial root. So what's left is still a polynomial. Now, what's left will be a polynomial. By this, I will put T here. So the Newton polygon here, it's the first, because all roots have trivial roots, the first has a slope 0. It's ordinary. So it starts with here, and then later on, the slope will be 1 or more. So the slope of other roots will be always at least 1. So that means that other roots are divisible by q. So the quotient is actually a polynomial in Qt, not just in T, and where PFT is a polynomial with integer coefficients of degree d of delta minus 1. So we have removed the one root, so the degree dropped by 1. Now, remember what's the relation between zeta function and L function? The zeta function, if we change the variable Qt, then this is the Toric part, trivial factor, times this L function. Right. So that's a relation. Now we want to replace by this primitive one. So we have to divide by this root and raise to this power to make it a polynomial. If you do that, so to do that, it turns out that there is I equal to 0, there is a factor of 1 minus t here. When I equal to 0, this is a negative 1 and minus 1, which is 1. So we move this trivial factor into there. So we start with I from 1 to n, that's the same factor. And here I would put it Lx0ft, divide, raise to negative 1 to nth power so that they get a polynomial, and then divide by 1 minus t. Of course, here I do not have negative 1 to the nth power. So you just put it negative 1 to the power there, get back again. And turns out the trivial factor we get is negative 1 to the n plus 1, and minus 1, I equal to 0, that is a minus 1. So indeed this trivial factor 1 minus t indeed can be moved into here and with this form. This one of course is then a polynomial, which is just our p f of qt. Now you see there's a qt everywhere. There's a qt here. Now is at least 1, so we can put one q in here with t. And here this is just pf qt. So now I can replace qt by t. Therefore, you get z f t. This will be okay. Now, after you move the 1q into t, your I will start from 0. And then this will be q to the I, t, and the exponent, you adjust the reindexing, this will give you n to the I plus 1. And what's left will be just p f t, negative 1 to the nth power. So the primitive part of this zeta function is really this polynomial pft. Of course, depending on the priority of the dimension, it could be in the numerator or it could be in the denominator. And if you want to count number of points, you just take logarithm of this one. So let me just rewrite this. So write f t here as a, so this is a polynomial of degree d of delta minus 1. So delta minus 2 if I start from 0. So it would be 1 minus beta I t. Then if you take logarithm, this gives the formula number of rational points of this alpha hypersurface of a K extension field. And this gives the contribution, which is the q to the k minus 1 to its power plus that's the main term and the trivial factor plus the non-trivial part of the error term. This is the error term from complex point of view. Of course, from periodic point of view, that could be the main term. In fact, this would be the error term is q. So this is true for all k. So this proves the formula which I described at the beginning of my lecture. So for zeta function, therefore, it remains to study this primitive part, which is a single polynomial. We need to understand this root beta. And similarly, you can define a primitive Hodge polygon, let's say, define it. Because we have removed the one trivial root, so what's left? Let's define the primitive Hodge polygon. PH, delta is, so draw a picture here. Slope 0, 1, 2, all the way up to n minus 1. So initially I started from 0, 1, all the way up to n for the Hodge polygon. Now it only goes up to n minus 1, and also I have removed the trivial root. So h0 is gone there. I start with h1. So this is really the primitive Hodge polygon, and this is the interesting part. And of course, then you have the results Newton polygon of this PFT is greater or equal to this primitive Hodge polygon. And everything I said previously is carried over to about the slope, carried over to here, because what I removed is a trivial factor. Okay, so I think I will stop here today, and maybe tomorrow I can discuss the sort of Newton, the slope, possible Newton slope symmetry under reflexive polytope.